directly coming out between you two.
Yes, and one actually that well, which is Sarah and me, and we haven't put it on. We haven't put it on archive yet.
Oh, there's a new one.
No, that's the only one.
Okay.
We put it on our websites, but we haven't put it on archive yet.
Yeah.
So how come
we had just one project in common.
Okay, well, looked interesting.
Yeah, we'll talk a little bit at the end about it.
Excellent.
It's yeah, it should be familiar to you. I mean, it's about non-local competition, so it's related to non-local FKPP.
Yeah, I was curious to see that.
So when will you end chairing actually? So
we're doing this this term. So we stop at the beginning of July.
Okay.
Yeah.
Okay. Cool.
And then it will be someone else for next fall.
You know who it will be?
No. We
volunteers are welcome.
Yes. I think there's we need to start actually thinking about it.
Yeah, we should start thinking about it indeed.
Oh, is it you who are finding the next one?
No, it's us plus the board.
Yes.
So
yes, if you go to the web page, there's an advisory board.
Yeah, I was actually wondering how the board interacts with you and what the board does. I mean, the board didn't, for example, check like the list of people that you invited, right? They didn't like issue a recommendation.
Hi, Peter.
Hello.
Hi, Peter.
Nice to see you, if only virtually.
Nice to see you.
Hi, Peter.
Hi.
We should give it a couple more minutes, right?
No, we're live streamed already.
Yeah.
Yeah, but we should start. No, we shouldn't start in advance.
Yeah.
But I think it's almost 4.
The number of participants has not stabilized yet. We should wait a bit more.
Yeah, I'm not sure one should wait for that. I don't in the lectures, definitely, but the lectures I have now are in the morning. I think this also, so in the end, I'm always surprised how many people are there, but not in the beginning.
That's what I was thinking when you said that you're extrapolating from lectures, right?
Yeah.
When I arrived in Oxford, I was starting exactly on time. And then after a couple of lectures, one courageous student came to me and said, you know that lectures are supposed to start at 5 past here. Anyway, okay, it's 1 past. I think we can probably get started. Okay, Pascal. So
all right.
Let me introduce you. So it's a great pleasure today to have Pascal Maillard and Sarah Penington, and we're going to start today's session with Pascal, who is going to talk about branching particle system and front propagation.
Yep. So thank you, Julien and Nina, for inviting me to give a talk here at the One World Probability Seminar. I'm actually very honored to be here. It's almost hard to believe that there was once a time where most of us were not even used to Zoom or to online talks. So I think when Leif and Andreas launched this seminar a year ago, they really hit a nerve. And you can see this from the impressive list of spin-offs they inspired. So I'm very happy that what started as an experimental project is now a firmly established venue. So again, thank you all, organizers and participants, for contributing to this great seminar. So my talk today aims to be a non-technical survey talk. I will present several recent results about branching particle systems and front propagation. This is an area that somehow sits between probability and PDE theory, but the methods I use are entirely probabilistic. So let me show you the list of people that I will mention during the talk, so collaborators of mine. So in the order of appearance in the talk, Jason Schweinsberg, who is from UC San Diego, Michel Pin, who is currently postdoc at Courant Institute. Then there is Gaël Raoul and Julie Tournière. So Gaël is a PDE theory, expert in PDE theory, and Julie is our common student. And there is Sarah Penington, who will give the talk just after me. And I also put here my student Fushuan Ho, so I will not directly talk about work with him here, but what he's currently working on is related to what I'm talking about. So please keep his name in memory. All right, so let me start by defining the model that will appear throughout the talk, which is branching Brownian motion. So in branching Brownian motion, particles move according to standard Brownian motion, and then from time to time they branch. So you can see this here in this picture. So a particle moves, and then here at this time it branches. So let's just say it branches into two particles, and these particles will now live their life independently from each other. And so each one will now again move and then branch after some random time into again two particles, and its children will again then live independently. Okay, so the branching times are exponentially distributed with rate 1/2. So if you consider only the number of particles in the system, then this is of course a continuous time Galton-Watson process, and it is supercritical, so the number of particles will increase exponentially in time. So at time t, the number of particles will roughly be exponential in t/2 because of the branching rate, which is 1/2. And if you look at the positions of the particles in space, then to first order, they will expand in a certain space-time cone. And the slope here, due to the choice of the parameters, is 1, right? So the rightmost particle will have asymptotic, or the topmost particle will have asymptotic speed 1, and the bottommost particle will have asymptotic speed -1. Sorry. Okay, so the PDE counterpart to what I've just presented is the Fischer Kpp equation, which was introduced, I think, independently by Fischer and Kolmogorov, Petrovsky, and Piskunov in 1937. So it's this equation here. So it's the heat equation with an extra term, which is this term here, which is also called the reaction term. So this is a nonlinear term, and its derivative at 0 is 1/2, so it's strictly positive. So if you look at solutions to this equation, so say with starting from some initial condition U0, then due to this reaction term, the solutions, if they're close to 0, they will be pushed up. And so if you start, say, initially with a condition which is 1, so which goes to 1 on the left and goes to 0 on the right, then the solution will have the tendency to move to the right. And so what happens is that there will be a stationary shape, which is also called a traveling wave, and which will move forward with a certain speed. So this is a common feature of what is nowadays called reaction diffusion equations. So the Fischer Kpp equation is kind of the most basic example in this equation, and in this class of equations, and these have lots of applications in many areas. So an area that I'm a little bit familiar with is population dynamics. So where it's an area in biology where you study the invasion of a certain species. So for example, of mammals, but can be many other species. So I warmly recommend you to look at the book by Shigesada and Kawasaki, where you can see lots of examples with real data. But historically, reaction diffusion equations have also been used, for example, in the study of propagation of flames and in many other contexts. So I've just said that the EFKPP equation is the PDE counterpart of the BBM. So there are actually two ways how you can relate BBM and FKPP. So the first one, which is maybe among probabilists the most well known, well, at least among those who work on BBM, is a certain duality relation. So this is an exact relation between the two equations. So for this, you look at certain product functionals of the branching Brownian motion. So, so these product functionals are of this form. So you take the product over all particles at time t of a certain function of the position of the particle. And now I also add a little x here. So think of starting the process at a point x. All right, so xu of t denotes the position of the particle u at time t, and nt denotes the set of particles at time t. So the function u defined by 1 minus this expectation now actually solves the FKPP equation. So for example, if you take u naught, so the initial condition in the equation, if you take it to be the indicator function of the negative interval, sorry, of the negative numbers, then UTX is the probability that the maximum particle is greater than little x. Okay, so it's 1 minus the cumulative distribution function of the maximal position. So this has been used by Bramson to give a very fine asymptotic of the maximal position. So as I indicated before, so the speed is 1. So to first order the maximum is at t, but it lags a bit behind. So it is of order log t behind t, and with a constant, explicit constant, which is 3/2, and then plus a capital O form. So this result was groundbreaking at that time, and so which it was obtained by PDE methods, and it's only fairly recently, so 10 years ago, it was obtained by purely probabilistic means by Elie Aydeco. And this has spurred many other results. So Julien has been involved in it about the study of not only the maximum, but of near extremal particles. So I won't have time to talk about these, but this has been an intense subject of interest in the last years. So the second relation between BBM and FKPP is the following. If you add a competition to the branching Brownian motion, so if particles kill each other, so for example, if a particle u kills a particle v at the rate 1/2n, according to the clock given by the local time at 0 of the difference in their positions, right? So particles kill each other when they meet, and in one dimension, it's very easy to define this. So you just take the difference of the positions and look at the local time at 0. and then you can kill particles according to this clock at a certain rate. So if you do this, then the stationary density of particles is exactly n. And so if you let n go to infinity now, then you can show that the empirical measure of the particles converges to the solution of the FKPP equation. So I'm actually not sure where this has been written first, but definitely it at least if you allow some well, it can certainly be deduced from results in Maillard and Fournier. So we study a more general class of branching systems with competition. And so many other models have hydrodynamic limits, which are maybe not exactly the FKPP equations, but equations which behave similarly. So you can also set up equations in discrete time or discrete space, but which behave similarly to the FKPP equation. And physicists, they speak about the FKPP universality class, so where things behave similarly to the FKPP equation. All right. So what I will be interested in is basically two things. So the first is finite n corrections, and the second is interchange of limits when n goes to infinity and time goes to infinity. So let me first talk about finite n corrections. So this is something that has been, I think, brought up by people in the physics literature. So these are the names here in the game. So Brunet, Derrida. So Brunet was a student of Derrida, Müller and Meunier, and Simon was also a student of Derrida. They had very influential papers on finite n corrections. So what am I talking about? If you think of the FKPP equation as the hydrodynamic limit of a certain particle system, well, then of course the solution takes values only at multiples of 1 over n, where n is like, think of it as the local particle density. What these people here, what these physicists said is that, well, this discreteness that arises here. So if you look at it at the front, then you can just treat it as a random noise of order 1 over square root of n. So why 1 over square root of n? Well, each particle contributes a noise of a variance 1 over n. And the number of particles is of order n. So, so the noise has variance of order 1 over n. So it is of order 1 over square root of n, right? And so they conjectured that the noise, the exact noise, doesn't actually matter. So some people have studied SPDE with a certain space-time white noise, but which is multiplied by a factor 1 over square root of n, and they have arrived at similar conclusions. And the conclusions are the following. So this noise, this random noise, so whether it comes from the discreteness of the system or some other noise, it has a very profound effect on the evolution of the front. So these effects, they are summarized here. So first of all, you have a correction in the speed. A speed correction. So as I indicated before, so without the noise, the asymptotic speed is 1. And with the noise, there is a correction which is actually fairly large. So which is polylogarithmic in n, right? It's not something like 1 over square root of n or 1 over n. It's actually, it's of order 1 over log n squared. Also, this noise, of course, makes the solution fluctuate. So let's say if you look at the the position of the front, meaning, for example, you fix the point where this solution equals 1/2. So say this point here, then this point will fluctuate. Will have fluctuations of order 1 arising on the time scale log n cubed. So again, a time scale which is fairly short, so which is again polylogarithmic in n. And maybe most strikingly, if you can define a natural notion of genealogy for such a system, so certainly for like a branching particle system, there is a very natural notion of genealogy, then they conjectured that this genealogy should be given by what's called the Bolthausen-Schnittmann coalescence. So I won't have time to talk exactly about, so to define what it is, but it's, if you're a little bit familiar with coalescence, so there is Kingman's coalescent, which arises as the genealogy of, for example, many mean field systems. And Kingman's coalescent can be constructed through Brownian motions. So you can think of it as an alpha stable coalescent with alpha equals 2. And Bolthausen-Schnittmann coalescent, you can think of it as a alpha stable coalescent with alpha equals 1. So it's kind of at the other end of the spectrum. And it has also arisen in statistical mechanics models. It's a very well-known object. So why is it so that this random noise has such a huge impact? Well, physicists would say it is because FKPP fronts are pulled. So what they mean by that is that the speed of the front is entirely determined by what happens here at the tail. So in other words, if you discretize the equation in such a way that the nonlinearity, you discretize, so you linearize the nonlinearity around 0, then the equation that you get has the same propagation speed as the FKPP equation itself. And therefore, it's somehow heuristic that it's somehow intuitive that if you perturb the equation at the front, then you have a big impact. All right. So let me talk about a work by Julien with his brother Nathanael and Jason Schweinsberg. So where they studied a model which gave so a toy model somehow which confirmed these predictions by the physicists. So they studied branching Brownian motion with a drift which is exactly minus the speed that I wrote down before, and where they kill particles at the origin. Okay, so think of the origin as the point where most particles are, and then by competition they're killed at the origin. So if initially we start with n particles distributed, for example, according to this density, which is roughly a stationary density for the system, then what they obtained is that, again, at time scale log n cubed, the number of particles in the system converges to a certain process, which is a certain continuous state branching process. So this is a limit of critical or near critical Galton-Watson processes. And the genealogy indeed converges to the Bolthausen-Schnittmann coalescent. And so the relation between these two processes, between inverse continuous state branching process and Bolthausen-Schnittmann coalescent, this was known before. So I just want to briefly mention the proof idea because it will also appear in later on. So there is a general theme in branching Brownian motion or branching random walks, which goes under the name of barrier techniques. So they arise, I think they have been introduced already by Bramson and his then PhD advisor Kasten. So let me explain what it means here in this context. So putting a barrier when people talk about putting a barrier in branching Brownian motion, branching random walk, what they mean is that you treat particles differently that hit this barrier than particles that don't hit this barrier. So let me say in 3 points what it means exactly. So the particles that do not reach this barrier. So let me just say, so here in this context, in this work by Berestiki, Schweinsberg, they put a barrier at a constant level, L, which is log n plus some correction terms. And so the particles that do not reach this barrier, so you can treat them by first and second moments. Then you have to, so this is the first step. Then there's a second step. You have to estimate the rate with which particles hit this barrier. And as a third step, you express the effect that particles have that hit this barrier. So because you choose this barrier exactly in such a way that the particles that hit this barrier will then have an effect, a measurable effect on the whole system at later times. And you can express this effect through a certain martingale that arises in branching Brownian motion without absorption, which is called the derivative martingale. I will say later a little bit more about it. Okay, so this is the basic idea in that paper. So the barrier technique that they use. And I adapted this a few years ago in a work originating from my thesis to so-called n branching Brownian motion, so which is branching Brownian motion where always the n topmost particles are kept. But I will not talk more about that. All right. So let me also say a little bit about a work which is very closely related to this, which is a work now on branching Brownian motion or branching random walk without absorption, but where this 1 to 3 scaling again appears, right? So I recall here that we have a 1 to 3 scaling. One is the, so when you consider space with respect to time, okay? The time scale scales as space to the cubed. And this scaling appears in other contexts. Whenever you look particles which are like close to extremal particles during the whole process. So, so this has also been called consistent or consistently maximal displacement by Fang and Zaitouni, and related work has been done by Jaffuel and Roberts. So what Fang and Zaitouni showed that if you look at the minimal distance that a particle will keep with the slope x equals t during the whole time of the process. So you look at the minimum over all particles at time t of the maximum of their distance to the slope. So in other words, you look at the smallest tube that you can put, or the smallest interval that you can put here such that there exists a particle that stays all the time in that interval, then the size of this interval scales as t to the 1/3. Okay, so the heuristic of this is actually very simple. If you consider the expectation of the number of particles that start at the top of such a tube and that end at the bottom of such a tube, then this expectation is roughly the product of two terms. It's the exponential in the size of the tube. So this comes from a certain Girsanov measure change. And then it's the probability that a single Brownian motion stays in such a small tube during time t, and this probability is roughly e to the minus a constant times t over lt squared. So if you want this to be of order 1, then you have to have lt of order t to the 1/3. All right. Good. So let me now talk about a recent work of mine with Jason Schweinsberg. So in this work, we took, again, branching Brownian motion with absorption, and we studied it at critical drift. So here we're considering drift -1. So it's the critical drift, and again, we kill particles at the origin. So you can maybe already guess that if you do this, then the system will die out, right? With weakly subcritical drift, the system also dies out actually with positive probability. And here with this critical drift, it definitely then dies out. And it's been understood already by Kasten at the end of the 70s that roughly speaking, the system of particles will evolve under a certain curve, which is, again, a curve which is a polynomial with exponent 1/3. So it's this curve LT of S, which is an explicit constant times t minus s to the 1/3. Okay, and so as I said, Kasten has had some first results on this model, and which were then greatly refined in another paper by Beresticki, and Schweinsberg. And what we showed with Jason is very precise limit theorems. So first of all, what we show, one example of what we show is the survival probability of the system. So we show that the probability that if you start from the top point here of this curve, or at distance 1 away from this top point of the curve, then the probability that you survive, that the system survives until time t, converges to a function of x, where x is here. Okay, so Beresticki, Schweinsberg showed this up to 2 multiplicative constants, and we showed the limit result. What you can immediately deduce from that is the law of the extinction time. So we show that the extinction time is of order t to the 2/3 away from t. And in fact, the extinction time minus t multiplied by t to the minus 2/3 converges in law as t goes to infinity to some explicit distribution. What we also study is a Jaglom limit. So what do you mean by that? We mean that we condition the system on an improbable event. So suppose we start, for example, with one particle which is like far below this topmost point at the curve, then the probability of survival until time t is small. And we show that if we condition on this time and look at the number of particles at time t, then this number of particles is of this order. Here is the exponential of, it's exponential in something of order t to the 2/9. And this term here is actually random. And we again give the exact, well, the asymptotic law of this term here, of this exponent. Right, so these are some examples of the results that we give. And the key tools here that we developed is, first of all, precise heat kernel estimates for Brownian motion in curved domain. So as I said before, so in these barrier techniques, so the first step is to control the particles that stay below the barrier by first and second moments. So these are expressed in terms of the heat kernel of Brownian motion in such a curved domain, and building up on results by Roberts, we gave very precise heat kernel estimates for domains, for curved domains such as this one here. So then we adapted the proof of Beresticki, Schweinsberg for the that I just mentioned for the system at near critical drift, we adapted it to establish the convergence of a certain quantity again to Neveu's continuous state branching process. So for the expert, actually the last steps in the proof are quite different. So if you at some point in your research you would like to show convergence to a certain continuous state branching process, you might be inspired by the method of proof that we gave here. And so this quantity allows to predict the extinction time in the future, and for this we build up on the previous estimates by Beresticki and Schweinsberg, which hold up to multiplicative constants that I mentioned before. Okay. So the next work I want to talk about is work with Michel Pin on fluctuations of extremal particles of branching Brownian motion. So this work was motivated by an article by, in physics by Maillard and Meunier, who had the interesting idea of adapting the methods that were invented for, or that were used to study finite n systems to the extremal particles of the usual branching Brownian motion, so without absorption, without selection. So at first, one might think that this is not possible. So for the following reason, if you look at extremal particles in branching Brownian motion, so for example, you look at the particle which is at the maximum at time t, and then if you look at the trajectory that this particle has performed until that time, then what you roughly see is a Brownian excursion, well, flipped upside down and with a linear slope added to it. All right. So in particular, so this is this red path here. So if you turn your head upside down, you can. This is a Brownian excursion in the limit. So which has actually been proven for branching Brownian walks by Chen. I think 2015. Xin Chen. So in particular, if you look, say, at time t/2, then the trajectory of this particle, so the ancestor of the maximum at time t/2, will have a distance from this slope, which is of order square root of t. Okay, so that's not the scaling that we've seen before, right? So here we have a space that scales as time to the power 1/2 and not to the power 1/3. So yet, what I've just presented, so the ideas that I've just presented, they can help not to study fluctuations of extremal particles which are of order 1, but which are of order 1/square root of t. So which is exactly the term that's missing. So this is the content of the series of 2 papers with Michel Pin. So here we describe fluctuations of order 1/square root of t of quantities which involve particles which are at distance square root of t away from the critical slope. So in order to express this, one can express this as follows. So consider the following random measure, mu t. So where we sum over all particles, what do we sum? We sum t minus the position of the particle. So we want to describe particles which are at distance square root of t away from this slope. So we look at t minus the position of the particle divided by square root of t. And then we weight such a particle by essentially an exponential in the position, but with this linear correction term. So why would one look at that? So if one considers, for example, just the mass of this measure, then this is an object which is well known. It's the so-called derivative martingale, which was introduced in this paper by Lally and Selke in '87. And it's been known since then that this quantity converges almost surely to a certain random limit, so which is called the derivative Martingale limit. This limit heuristically describes the fluctuations that appear at the beginning of the branching Brownian motion. Right, so simply because, well, this stabilizes to a limit, and then conditioned on the infinity, you can think of the branching Brownian motion as a system which has now much less fluctuations and which is shifted by the log of this derivative martingale. So in particular, what Maillard showed is the following. This random measure mu t converges in probability to a multiple of a certain deterministic measure, and the multiplicative constant is simply z infinity. All right, so so this deterministic measure is nothing else but the law of a Bessel III process at time 1 starting from 0. So very explicitly, it's this measure. So this was shown by Maillard. And what we established with Michel is the first term in an asymptotic expansion of this measure mu t in 1 over square root of t. So disclaimer, this is not how we wrote it, because we wrote it in terms of the integrals of this measure against test functions, but heuristically that's what is written. So this mu t can, so the first order in the expansion is what I've just written, right? It's c infinity times this measure mu. Then there is a next order term which is deterministic. It's some deterministic density times log t over square root of t. And then there is a random part here, so which is of order 1 over square root of t. So it's a superposition of this measure mu with rescaled versions of it. So this here is the push forward of the measure mu by multiplication with square root 1 minus s. And so this superposition with has weights or amplitudes which are random. So here this is an integral against a totally asymmetric one-stable Levy process. So which is independent of z infinity. And so with the time change here, you look at s of z infinity divided by square root of u. All right, so the basic take-home message is that the next order term in the expansion of mu t in 1 over, so mu t admits an expansion 1 over square root of t with some additional corrections which are of order log t over square root of t, and probably other log terms should appear later on. And the first interesting term is this one here. It's a random term, which is a random superposition of these rescaled versions of this measure mu, and which has a one-stable, totally asymmetric one-stable Levy process appearing. So as I said before, so the result is in reality stated in terms of integrals against test functions. So we also show actually functional convergence here. So we can take the measures at different times, say t1, t2, t3, which are all at scale t, and get joint convergence. And I want to point out some related results. So there has been a recent result by Mitnick, Rijik, and Roque-Joffre. So where they studied also one-stable fluctuations which appear directly in the extremal point process, which arises in a t to infinity limit when you look at particles near the maximum. And this was established by purely PDE means. And there are also several works So here are authors that were involved in it that consider fluctuations of branching random motion or branching random walk, but which are rather in the bulk of the system.
Pascal, can I?
Pascal, there's a question in the chat.
Yeah, exactly.
Okay.
So
Yes.
there is. Does the convergence rate of the limit? Does this give the convergence rate of the limit in the previous slide? Is the question.
Yes, exactly. So the convergence rate is exactly. So so as I said, how we state it rigorously is that we integrate this measure against a certain class of test functions, which are actually allowed to have a pretty nasty singularity at the origin. So they're allowed to explode like 1 over x to the alpha near the origin with alpha less than 2. And so these integrals against these test functions, they converge at rate 1 over square root of t with this additional log t over square root of t correction. Yes, that's right. Does that answer the question?
Yes. Yes.
Okay.
Thanks.
Good. Yeah. Thanks for the question. All right. Let me give a brief sketch of the proof. So first of all, let me recall that that's what I wrote 20 minutes ago. If you look at the typical position of the maximal particle at time t, then this is t minus 3/2 log t. So that's Bramson's and Idegons result. Still, what has been known since the work by Hu and Xi, and then there is a very precise version of it in Hu, is that from time to time there are particles that reach higher than that. So from time to time there are particles that reach up to t minus 1/2 log t. And these are exactly the particles that cause these fluctuations of order 1 over square root of t. So in order to catch these particles, what do we do? Of course, barriers. So I won't put in exactly the barriers that we put, but the basic idea is again to put in a barrier to treat particles that are below the barrier by first and second moments, and to estimate the rate with which particles hit the barrier and to treat them separately. So the problem here is that we can do it, but we cannot do it in just one single step. So actually, in order to do this, so there are at least 2 problems. The first is that there are many particles actually reaching such a barrier at earlier times. And so these we have to treat, we don't only have to deal with an order 1 number of particles, but actually with many. And also these first and second moments, we're not able to directly get a very precise enough estimate on these. So we actually need to look at all intermediate timescales t to the alpha, where alpha is in 0, 1. And so how we get around this is by a bootstrap or multiscalar amplification argument, as you wish. So so very roughly speaking, we first get a first estimate on the rate of convergence of the quantities that I mentioned before, which is not good, which is maybe t to the minus 1 over 10. And then we use this estimate to the intrinsic hierarchy of the process to amplify this estimate. So we apply this estimate to the particles that hit the barrier, and we also apply this estimate when we calculate conditioned first moments of quantities at time t conditioned on a time which is t to the alpha. All right. So I won't go into more details here, but I think examples where such multi-scale arguments are used in branching processes are not, they're not, at least not in branching Brownian motion, are not that many. So I'd be happy to have your comments on this. Okay. Are there any questions, more questions about this point here, or what I talked about before? Okay, so if not, then let me talk about the second thing that I wanted to mention. So as I said before, what I will be interested in is finite n corrections and interchange of limits, n and time, so number of particles and time. And this is particularly interesting when you consider branching particle systems with competition. So I will now talk about the recent work with Gaël and Julie, where we considered a branching random walk again. So we could have considered branching Brownian motion actually with the competition that I mentioned before, but for some reasons we consider branching random walk again on a one-dimensional space, so on a lattice, and with on-site competition. So think of the competition that I mentioned before, but we allow for more general rules of competition. So you can think, for example, of the very simple one. If at some site there are more than n particles, then we just kill the surplus. What is now different is that we consider a branching rate which depends on space and time. So a heterogeneous branching rate, and we choose the heterogeneity on a certain macroscopic scale. So the scale is 1 over epsilon, so it's the scale both in time and space, and so the branching rate is a function of epsilon times the time and epsilon times the space x. So now you can consider two limits. You can consider the limit first as n goes to infinity. Then again, you have a hydrodynamic limit, which is a certain FKPP type equation. And you can consider also the limit space and time scale goes to infinity. And then you can ask, what's the asymptotic spreading speed? So for us, it will just be the first order of, say, the rightmost particle. And the question is whether the limits commute. And since I'm asking this question, of course, you can guess the answer. In general, no. So let me first show you what happens, when we first let n go to infinity and then epsilon go to 0. So as I said, we arrive. Yes, Julien?
What type of assumption do you have on your function r?
Sorry, can you say it again?
What does your function r look like? What does the branching rate r?
Okay, thanks for asking. It's a smooth function, and say bounded between two constants and with bounded derivative, right? So nothing weird, nothing wild. So this is not homogenization. This is heterogeneity, which is on a large scale, not on a microscopic scale.
Okay, thanks.
All right. So if we let first n go to infinity, then epsilon go to 0. Sorry, if we first let n go to infinity, then as I said, we arrive at a hydrodynamic limit, which is a FKPP type equation. So just for the sake of definiteness here, think that it is exactly the FKPP equation. So which is the derivative in time is, so as what you saw before, so 1/2 second derivative in space. Then here, this is the reaction term. So which, if in the case when, for example, you kill the surplus when you have more than n particles, would be just this function here, u times the indicator u less than or equal to 1. But nothing will change in what I will just say if you consider the nonlinearity that we had before. But the point is that this reaction term is now multiplied by the branching rate. so now it's a very classical fact in the PDE literature that when you take now this equation and let epsilon go to 0, then you arrive at a certain Hamilton-Jacobi type equation in the limit. So if you change variables like that, so you may think of it as a Hopf-Kohl transform. So u is exponential minus so some new function v divided by epsilon, and now this function v also there is a change of variables in the arguments. Then this function v converges as epsilon goes to 0 to the solution of a certain Hamilton-Jacobi type equation, or to be more precise, a variational inequality. So this was shown, I think, first by Freitlin in '85, so with probabilistic methods actually, and not using this representation, but the associated variational representation of this solution. And it was shown by Evans and Souganidis using the theory of viscosity solutions to Hamilton-Jacobi equations. So in particular, if you're interested in the position of the front, so the point where the solution goes from being above 1/2 to below 1/2, then this front position converges to a certain function, which I call xhj of t, and which is also can be expressed in terms of this v. So it's the rightmost point where this function v equals 0. So in graphics, so here's one example where you have here in this region in space, you have a favorable region where this r is high. And what can happen here if you plot this v, so this function v, so this is v at some time t1, and this is v at a later time t2. So remember that v positive means that the solution is exponentially small there, and v equals 0 means that the solution is of order 1. So what can happen here is that if you have a certain region here, then the solution, the right boundary of the support can actually have a jump, right? So here the right boundary of the support is here, and then this part here goes down, and then the right boundary of the support has a jump. So things like that can occur. So this function here actually can be non-continuous. So in contrast, what we show with Gael and Julie is that if you take the original system, so the n particle system, and define the position of the rightmost particle to be RT of epsilon. And if we now take the other limit, so first let epsilon go to 0 and then let n go to infinity, then we arrive again at a certain function x of t, but which is now not defined in terms of a Hamilton-Jacobi equation, but is simply the solution of a certain ODE. And it can be shown that this function is always smaller than the other solution than the xhjt that I defined before, and in general the inequality is strict. In fact, this ODE can be seen as arising from a certain degenerate version of the Hamilton-Jacobi equation. So we also conjecture that there is an interpolation regime which appears exactly when epsilon times log n is of order 1, so is bounded away from 0 and infinity. Sorry, so this should be alpha between 0 and infinity. So this is might be subject of future work. All right, so I also wanted to talk very briefly about work with Sarah Penington on branching and walk with non-local competition, but I fear that my time is running out. So Sarah, I hope you don't mind if I skip this part. So the slides are online, so and the paper is also online. So I hope that it will still be of help to some people. Okay, let me just conclude. So I want to conclude with an outlook. So what I'm currently interested in is, for example, branching Brownian motion with heterogeneity in space and time at macroscopic scale. So you've just seen an example, but there are other examples. And one particular example which I like is when you take a branching random walk or branching Brownian motion, which is only heterogeneous in time, then this has been proposed by Derrida in the 80s as a toy model for spin glasses. And with Luigi Addario-Berri, sorry, we studied the problem of finding algorithms that find particles at high positions in such a time heterogeneous branching random walk. So we established in this work an algorithmic hardness threshold. And the thesis of Fu-Xuan Ho, of my student Fu-Xuan Ho, deals with the problem of not just finding some particles at high positions in time heterogeneous branching random walk, but of typical particles, so sampling efficiently according to a certain Gibbs measure. So there should be a first work coming out soon, so I wanted to advertise that. And this problem and other problems are part of a project with Lisa Hartung, Project Remico, so funded by ANR and DFG. And I warmly welcome you to look at the website and check out for updates on this project. Okay, thank you so much for listening.
Thank you very much, Pascal, for this lovely talk. So are there any questions for Pascal before we thank him altogether? You can either unmute yourself or ask in the chat. So I have a... No. Okay. Can you hear me, Pascal?
Yes.
Okay. So I was wondering about this really nice work with Raoul and Julie. So what happened? So I think there's there's been a lot of work from the PD community on the speed of propagation for KVP like equations in heterogeneous environments. And so I was thinking of a function R, which does not really depend on time, which is constant in time, but maybe where you have something which is like a sinusoid around 1 with amplitude epsilon. So what happens then? Is there can you say something about is there a slowdown?
So can you say it again? So this function R, so I'm not aware of these works, I have to admit.
I'm thinking of a function R with some frequency, which is going to oscillate around 1, okay? Which have like regions of high production and region of lower production.
Yes.
But this is like with a vanishing, with a parameter, 1 plus theta and 1 minus theta, and then I'm thinking of theta as being small. And I'm guessing there is going to be a slowdown with eta, and probably So what is, do you know what is known in terms of the slowdown for the particle systems?
I'm aware of. So we actually did a. So one example of application, and where we also have numerical studies, but there has been explicit work on it, is where R is not a sinusoidal function, but is really constant. Stepwise constant, so it oscillates between two constants. But here the oscillation is large and not small. And what happens is, if the oscillation is sufficiently large, then this xhj of t can have jumps. And I think, is it the case that for any difference between them, x is always difference to xhjt? Then this I don't know.
What is it that the particle system stays in those like rich environment, and then you have to wait a random time until one particle makes a jump to the next one?
Well, this would be, yes, in the limit probably when you let the difference between these two environments when you let it go to infinity, maybe.
Okay.
Very interesting. So if the difference is very large, then what happens is exactly what I wrote here. So the solution of the FKPP equation is always positive, but can be exponentially small. But if it is exponentially small in a very favorable region, then it will blow up there quite quickly, and then it will overrun what well, and then it will cause a jump in the position of the front. So this happens. So I'm sorry. I'm not able to answer your question about well, when the fluctuations are small and effective slowdown. So I can't answer that.
Okay. Well, thanks. So I suggest. I mean, are there any other questions? I'm hearing a mic rattling, but no questions. Okay, so in that case, I suggest that we all unmute ourselves and we thank Pascal. And we'll take a few minutes break and start again. What time do you want to start again, Nina?
10 past.
10 past. Okay, let's reconvene at 10 past. You want to stop sharing, Pascal?
Yeah.
Wow, it was quite a lot in there.
So when you say this, then you mean it was too much?
No, it was good, actually. It was very nice. We liked it. Excellent.
Yeah,
oh,
thanks.
I need to copy your link, Sarah. Let me do it now. Okay, get link.
So you can see my slides, I assume? Yeah, great.
Working perfectly.
And what time should I try to stop?
I mean, if you go a little bit over 4, I think over 5, it's okay, I think.
Okay, I will.
Yeah, you should aim for 50, 55 minutes. So Pascal, at what point is what is Julie's status at the moment? If you are still here.
You're muted.
Yeah, she's looking for a job.
Okay, she's already defended her thesis?
No, she's in 3rd year, so she will defend by the end of the year, I guess.
I'm trying to work out which wall in Oxford Nina's background photo is from. She said it's a wall in Oxford.
Oh, really?
But I'm not sure that I recognize it.
Really? Let me see. It's in Oxford.
Well, that's what she said, yeah.
I think it's in front of the department, you know, where there is the.
Well, yeah, I was wondering that, the one with the dinosaur graffiti,
Yeah.
but I don't know. Can you see my mouse? The little hand thing.
You can see an arrow. Well, I can see an arrow.
Yeah. Okay. Oh, that's okay. Maybe it looks different on my screen. Oh.
Can you move it because it's not moving?
Yeah, I'm moving it.
No.
So it's not. It's not moving.
No.
Okay, that's no good.
Maybe it has a delay.
It's still not moving.
No.
No.
That's annoying.
Oh, it is above the eye of infinite, and it's not moving.
Are you meaning to be full screen?
Yes.
Because I'm not seeing full screen. I'm just seeing.
Oh. That's odd. Maybe I'll stop sharing and try again. Oh, hang on. I think I've managed to pause this. Okay. Okay, I'm going to stop sharing and try again.
That's better.
That's better. Yeah.
Yeah, and now you can see something moving.
Yeah.
Yeah.
Now we see the mouse. Yeah.
Okay.
Very good. Okay, I think it's 10 past. So we reconvene. So our second speaker is Sarah Penington from Bath, and she will tell us about Brownian bees in the infinite swarm limit. The screen is yours already, Sarah.
So thank you very much for the invitation. I'm also very happy to talk at this seminar. So today I want to talk about a particle system and a related PDE called a free boundary problem. And I want to try and show you what we can prove about the particle system using the connection to the free boundary problem. And this is all based on joint work with Julien Barré-Sticky, who's at Oxford, Eric Brunet, who's at the ENS in Paris, and Jim Nolan, who's at Duke. So this is the particle system that I'm mostly going to be talking about. So we call it the Brownian bees process, but you could also see it as a d-dimensional n-particle branching Brownian motion. So we've got n particles that are moving around in Rd according to independent Brownian motions. And each particle is also carrying with it a clock that has an independent amount of time on it that's exponentially distributed with rate 1. And at the end of that time, so when the clock rings, then the particle branches into 2 particles. But each time a particle in the system branches, then the particle in the system that's furthest from the origin is killed. So we have a constant number n of particles in the system at all times. So in the pictures on the right, I'm going to show you what could happen if we were looking in at the case d equals 2 and n equals 5. So we'd start with some particles in R2, and they're going to move around according to two-dimensional Brownian motions until one of them tries to branch. So that might be this blue one here. And then we see which particle is furthest from the origin. So that would be this particle, that particle is killed, and then the blue particle is allowed to branch into 2, and the other 3 particles just continue to move as Brownian motions, and so on. So we always have 5 particles in the system at all times. So this is the particle system that I'm mostly going to talk about for most of the talk. And then towards the end, I'm going to talk about some related models and some conjectures related to our main results about this Brownian bees process. And I should say that throughout the talk, the Brownian motions are going to have diffusivity square root of 2, so they're going to be sped up by a factor of 2, and that's just to avoid having some coefficient halves in front of Laplacians in the PDEs. And a bit of notation, I'm going to write xn of t for the vector of particle positions of the particles in the Brownian bees at time t. And I'm going to write mn t for the maximum distance of a particle from the origin at time t. So the maximum over in1 up to n of the norm of xin of t. And I'm going to write mu n of dx and t for the empirical measure of the particle positions at time t. So we'll give a mass of 1 over n to each particle, and then we'll sum from k equals 1 to n, and we'll have a point mass at the location of each particle. So as I said, this particle system is closely related to a free boundary problem. And this is the free boundary problem. So let's suppose we have an initial probability measure mu naught on Rd, and then we've got a pair of unknowns, u and r. So u is a function of x in Rd and time t, and r is just a function of t, so r is an unknown moving boundary. And we want them to solve this system of 4 equations. So we want u to solve this PDE for norm of x less than RT, and we want u to satisfy this boundary condition at distance RT from the origin. We want u to be 0. We want the integral of u at all times t to be equal to 1. And then we want the initial condition in a suitable sense to be given by the probability measure mu naught. And it's going to turn out that roughly speaking, we can think of u as being the density of particles in the Brownian bees process when n is very large. And we can think of RT as being roughly the maximum distance of a particle from the origin at time t. So then why do we end up with this system of equations? Well, for the first equation, if we're less than distance RT from the origin, then particles are only being killed if they're the furthest particle from the origin. And so in this region, particles are just happily moving around according to Brownian motions and branching, and they're not being killed. And so we get the Laplacian u term from the motion according to Brownian motion, and we get plus u from the particles branching into 2 particles at rate 1.
There's a
question in the chat.
Okay.
And the question is if mu naught is assumed spherically symmetric.
No, we don't assume that. So it could be, but we're not assuming that. Yeah. So the second equation makes sense because if particles are at distance roughly RT from the origin, then they're being killed. And so we should expect the density of particles there to be 0. And then the third equation is essentially saying that the integral of the density or the total mass of particles is constant and equal to 1. And that's because the total number of particles in our system is constant equal to n. So the first thing that we need to establish about this system of equations is whether solutions actually exist. So it turns out that solutions exist and they're unique. So we can show that for any Borel probability measure mu naught on Rd, there's a unique global solution u and r to the free boundary problem. And for this solution, then RT is finite and continuous for all positive times t. And if you let t go to 0, then RT converges to R0, which is given by the infimum of positive R, such that mu naught of the ball of radius R centered at the origin is equal to 1. So for example, if mu naught was a point mass at the origin, then this R0 would be 0. And if mu naught had unbounded support, then this R0 could be infinite, but then RT immediately becomes finite at all positive times. So as I said, this is going to turn out to be roughly the density of our particle system when n is very large. So this is our first main result about the particle system, and it's a hydrodynamic limit result. So let's suppose that mu naught is a Borel probability measure on RD, and let's suppose that our initial particle locations are IID with distribution given by mu naught, and let's let U and R be the solution to the free boundary problem on the previous slide with initial condition given by mu naught. Then what we can say is that if we fix a time t and we take a measurable subset A of RD, then if we look at mu n of A and T, so if you remember that mu n was the empirical measure of the particle system, so mu n of A and T is the proportion of particles at time t which are in the set A. So we can show that mu n of A and T converges almost surely to, as n tends to infinity, to the integral over the set A of U at time t. And we can also show that mnt, which is the maximum particle distance from the origin at time t, that converges to RT, the position of the free boundary at time t, as n goes to infinity. So essentially what this is saying is that if we fix a time t and we let the number of particles n go to infinity, then the density of particles is converging to the solution of the free boundary problem at time t. And I'm trying to summarize that in the green boxes at the bottom of the slide.
Sarah, there's another question in the chat again about mu naught. If mu naught is assumed to have the first moment.
No, we just assume that it's a probability measure, that it's a Borel probability measure. Yeah. So this is telling us if we fix a time t, then what our particle system looks like if we let n go to infinity. But what we'd really like to understand is the long-term behavior of the particle system for large n. So we'd like to be able to fix a large n and let t go to infinity and understand what the behavior of the particle system looks like. So maybe a sensible first step would be to understand what happens to solutions of the free boundary problem if we let time t go to infinity. So it turns out that solutions of the free boundary problem converge to a steady state solution. So we're going to let capital U and R infinity solve this system of equations. So capital U is just a function of x in RD, and R infinity is an unknown constant. And we want them to solve this PDE for norm of x less than R infinity, and we want U to be positive in that region, and then we want U to be 0 at distance R infinity from the origin, and we want the integral of U to be equal to 1. So there's a unique choice of R infinity such that these first three equations have a solution, and then that solution is unique up to a scaling factor, and the last equation tells us what that scaling factor has to be. So this is a steady state solution of the free boundary problem, and it turns out that solutions of the free boundary problem converge to this steady state solution. So if we take any initial Borel probability measure mu naught, then the solution U and R of the free boundary problem converges to capital U and R infinity, in the sense that if we take the limit as t tends to infinity of RT, then that's R infinity. And if we take the L infinity norm of the difference between U at time t and capital U, then that goes to 0 as t goes to infinity. So again, I'm trying to show that in the right-hand boxes on the slide.
So that's there's another question in the chat. What happens to the MNT, so to the maximal distance when t goes to infinity and n is fixed? Can you say something about that?
So can I answer that by the next couple of slides? There will at least be some
Of
information
course,
about that.
of course.
Yeah. So yeah. So now what I'm going to do is go back to the particle system. So let's fix n and see what happens as t goes to infinity. So it turns out that the process xnt has a unique unit invariant measure that depends on n. So we can call it pi n, and it's a probability measure on rd to the n. And for any initial particle configuration, the law of xnt converges in total variation norm to pi n as t goes to infinity. So if we take the supremum over subset C, a real measurable subset C of rd to the n, of the modulus of the probability, the difference between the probability that the particle system at time t is in C and pi n of C, then that supremum goes to 0 as t goes to infinity. So now the natural question to ask is what happens to this stationary distribution pi n as n goes to infinity? So as n goes to infinity, does the shape of the cloud of particles under pi n converge in some sense to the stationary solution of the free boundary problem? Or in other words, is the long-term behavior of the particle system for large n the same as the long-term behavior of the of solutions to the free boundary problem? And the answer is yes. So this is what we can prove. So if we take a small positive epsilon and we take a subset A of Rd, which is a measurable subset, then if we take the pi n measure of the set of particle configurations such that the proportion of particles that are in the set A is more than epsilon away from the integral of capital U over the set A, then the pi n measure of that set of configurations goes to 0 as n goes to infinity. And also if we take the set of particle configurations such that the maximum particle distance from the origin is more than epsilon away from r infinity, then the pi n measure of that set also goes to 0 as n goes to infinity. So essentially what this is saying is that if n is very large, then under pi n, with high probability, the density of particles is roughly given by this steady state solution capital U, and the maximum distance of a particle from the origin is roughly r infinity. So those are our main results about the Brownian Bees process, and I'm sort of summarizing them at the bottom of the slide. So what I'm going to try and do now is tell you a bit about some ideas from the proofs of these results, and then at the end I'm going to talk about some related models and some conjectures that are related to this set of results. Was that something else in the chat?
It was answered already.
Okay, great. It's very useful having collaborators in the audience. So now I'm going to move on to talking about some ideas from the proofs. So essentially the idea in most of the proofs is to first just think about distances of particles from the origin rather than actually the locations of the particles in Rd. So we're going to let Fn of r and t be mu n of the ball of radius r centered at the origin and t. Or in other words, Fn of r and t is the proportion of particles that are within distance r of the origin at time t. And it's going to turn out that if n is very large, then Fn is roughly the solution of a one-dimensional free boundary problem. So this is the one-dimensional free boundary problem. So we've got an initial condition v0, and we've got a pair of unknowns. So v is a function of r, a distance r in a time t, and r is just a function of t. And we want them to solve this system of equations. So we want v to solve a PDE for r between 0 and rt, and we want v to satisfy a couple of boundary conditions at rt and another boundary condition at 0, and then we want it to have initial condition v0 in a suitable sense. So as I said, it's going to turn out that we can think of v of r and t as being roughly Fn of R and T when n is extremely large. So why do we end up with these equations? Well, for the first equation, if R is less than RT, then we're thinking about particles at distance less than RT from the origin. And so it'll turn out that, as before, we can think of RT as being roughly the maximum particle distance from the origin. So these particles are not being killed, they're just happily moving around as Brownian motions and branching. And so for the case d equals 1, then we'll just get this Laplacian term from the Brownian motion and a plus v from the branching. And then for general d, the distances of particles from the origin are Bessel processes. And so the extra drift away from the origin that you get in the Bessel process gives us this extra middle term. And then this first boundary condition is just saying that the proportion of particles that are within distance RT of the origin at time t is equal to 1. And that makes sense because we're thinking of RT as being the maximum particle distance from the origin. And then the next boundary condition is saying essentially that the density of particles at distance RT from the origin is 0, which makes sense because particles are being killed at distance roughly RT from the origin. And then this fourth equation is just saying that the proportion of particles within distance 0 of the origin is 0. So first of all, we need to get existence and uniqueness of solutions to this free boundary problem. So we can show that for any measurable V0, then there's a unique global solution V and R to this free boundary problem. And actually the way that we show this is we have a sequence of solutions to PDEs that don't have a free boundary. So we have solutions to these PDEs that all have different nonlinear terms, so Vn minus Vn to the power of n. And the only boundary condition that they have is at 0, and then they all have the same initial condition. And it turns out that if you let n go to infinity, then these solutions converge pointwise, and they converge to a solution of this free boundary problem. So that's how we prove existence of solutions to the free boundary problem. And when we've got this existence and uniqueness result for the one-dimensional free boundary problem, we can use that to get our existence and uniqueness result for the original d-dimensional free boundary problem. So if we take mu0 to be the initial condition that we want for our d-dimensional free boundary problem, if we let v0 of r be mu0 of the ball of radius r, then it turns out that so if we then take the solution to this free boundary problem, then the free boundary RT that we get is the correct free boundary for the d-dimensional free boundary problem. And so essentially then we've done all the hard work in constructing a solution to the d-dimensional problem because we found what the free boundary should be. So that's existence and uniqueness to this free boundary problem. But then we can also prove, so what we can prove is essentially a one-dimensional hydrodynamic limit result. So we can show that there exists a positive constant C1, such that if n is sufficiently large, then if we fix a time t, then if we take an initial particle configuration xn, then let's let Vn and Rn be the solution of this one-dimensional free boundary problem with initial condition given by this initial particle configuration. So we want V0 of R to be Fn of R and 0, or in other words, V0 of R is the proportion of particles at time 0 under the configuration xn, which are within distance R of the origin. So once we've got this solution of the free boundary problem, which is just a function of our initial condition xn, then what we can say is that so I'm going to write p subscript xn to mean that I'm starting with initial particle configuration xn. So we can say that the probability that the supremum over R of the difference between Fn of R and T and Vn of R and T, the probability that that's at least e to the 2t times n to the minus c1 is at most e to the t times n to the minus 1 minus c1. Or in other words, with very high probability, if n is extremely large, then with very high probability, Fn is very close to Vn. So what's going to be useful later on is that this probability bound doesn't depend on our choice of xn. So xn determines the solution of the free boundary problem Vn that we compare Fn to, but it doesn't affect this probability bound. And the way that we prove this result is using couplings that are inspired by proofs of De Masi, Ferrari, Prosutti, and Soprano-Loto. So I'm going to talk a bit more about their results later on. But essentially, these couplings allow us to sandwich our particle system between two particle systems that are easier to control. So our Brownian Bees particle system, each time a particle branches, another particle is killed. But the particle systems that we sandwich between, they have short time intervals where the furthest particles from the origin are killed either at the start or at the end of those time intervals. And so those particle systems are a lot easier to control, and that allows us to prove this result.
There is a question in the chat, Sarah.
Yep. So there's do they mean L2 norm as in that the distance from the origin is L2 norm? So if so, then yes. So we do rely on yes. So you could, for example, come up with a particle system where you killed particles that were furthest away from the origin in an L infinity or an L1 norm. So yes, so we think that we don't think that we can immediately handle those kind of cases yet, but that would be extremely interesting. Does that kind of answer your question?
Yeah,
okay.
I see.
Yep. But yes, I'm definitely assuming that distance, when I say distance from the origin, I mean L2 distance all the way through this. So now I want to try and show you how we can prove our d-dimensional hydrodynamic limit from this hydrodynamic limit that's only about the particle distances from the origin. So at the top of this slide, I'm trying to remind you of the setup for the hydrodynamic limit theorem. So let's suppose that mu naught is a probability measure in RD, and our particle locations at time 0 are IID with distribution given by mu naught. And we suppose that U and R is the solution of the free boundary problem with initial condition mu naught. And let's suppose that V and R is the solution of the one-dimensional free boundary problem with initial condition given by mu naught of R is, sorry, V naught of R is mu naught of the ball of radius R. And as I mentioned before, so if you take this initial condition V naught that depends on mu naught in this way, then these two free boundaries are the same. So I'm not cheating by calling both of these R. And what we want to show to get the d-dimensional hydrodynamic limit is that if we take a subset A of RD, then we want to show that mu n of A and T, so the proportion of particles at time t that are in the set A, converges to the integral over the set A of U at time t, almost surely as n goes to infinity. So the main intermediate result that we still need to get this is an upper bound on MNT, the largest particle distance from the origin, that holds uniformly over a time interval. So what we show is that there's a positive constant C2, such that if we take a small eta, then if n is sufficiently large, depending on eta and t, then the probability that there exists a time t in the time interval eta up to capital T, such that MNT is bigger than RT, the position of the free boundary at time t, plus eta, that probability is very small. So essentially we're showing that on this time interval with high probability, the maximum particle distance from the origin is at most the position of the free boundary plus a little bit. And the reason that we've got this eta here rather than 0 at the start of the time interval is that it's quite hard to control the behavior of RT for very small values of t. but this turns out to be enough for proving the d-dimensional hydrodynamic limit. So how do we prove this? Well, I'll just try and give you a very rough sketch of how we prove this. So using the result on the previous slide, the one-dimensional hydrodynamic limit result, we can say that if we take a time s, then Fn of Rs and S is with high probability going to be very close to Vn of Rs and S, where Vn is the solution of the one-dimensional free boundary problem with initial condition determined by the initial particle configuration. But then Vn has initial condition given by, so the initial condition at distance r is given by the proportion of particles within distance r of the origin at time 0. And because we're assuming that particles are IID with distribution given by μ0, then actually the initial condition will be very close to μ0 of the ball of radius r. So that means that Vn is actually very close to V, and by definition, V of Rs and S is equal to 1. So with high probability, Fn of Rs and S is very close to 1, which means that almost all of the particles at time S are within distance Rs of the origin. But then in a very short amount of time later, so those particles are going to continue to branch. And so a very short amount of time later, then these particles can branch enough to have at least n descendants. And so that means that particles that at time s are further than, say, Rs plus half eta away from the origin, those are very quickly going to be the furthest particles from the origin, and so they're going to get killed off because they won't be able to move very much in a very short amount of time. So we can show that on a very short time interval soon after s, then with high probability there won't be any particles that are further than RT plus eta away from the origin. And if we sort of add up the results over lots of little time intervals, we can get this result. So once we've got this result, then how do we prove the d-dimensional hydrodynamic limit? Well, what this result lets us do is compare our Brownian Bees process to a system in which particles are killed if they are a deterministic distance away from the origin. So what this proposition says is that with high probability, the largest particle distance from the origin is always at most RT plus eta. And so any particle that goes further than this from the origin is going to be dead. And so with high probability, our Brownian Bees will be a subset of a particle system in which particles are killed if they're ever at distance more than RT plus eta from the origin at time t. And this kind of particle system is much easier to control than the Brownian Bees, because once particles branch apart, then they behave independently. So it's not too hard to show when eta is really, really small that we get approximately the hydrodynamic limit result for this system, and then we can transfer that back over to the Brownian Bees system. So that's roughly how we prove the d-dimensional hydrodynamic limit result. So now I want to say a little bit about the proof of the long-term behavior of the solutions to the free boundary problem. So again, we start by proving a result about the one-dimensional free boundary problem. So we're going to let capital V of R be the integral over the ball of radius R of capital U. So if you remember that capital U was the steady state solution of the d-dimensional free boundary problem. And it turns out that solutions of the one-dimensional free boundary problem converge to capital V. So what we can show is that if we take a small positive c and we take a positive k and we take a small positive epsilon, then there's a time t epsilon that depends on c and k, such that if we take any initial condition v0, which is non-decreasing and satisfies v0 of k is greater than or equal to c, then if we take a time t that's greater than or equal to t epsilon, then so if V and R is the solution to the one-dimensional free boundary problem with this initial condition V0, then we can say that V at time t is at most epsilon away from capital V, and the position of the free boundary R at time t is at most epsilon away from R infinity. And so it's going to be important later on that we only need this condition, V naught of k is greater or equal to C, to know how quickly this convergence happens. And if we think in terms of our hydrodynamic limit result, then we were taking the initial condition for our free boundary problem to be, so V naught of R was the proportion of particles within distance R of the origin. So here, essentially, what we're saying for a particle configuration is that we want at least a little proportion C of particles to be within some big distance K of the origin. And the way that we prove this result is we just have to establish the result for two special initial conditions. So V naught plus, which is 1 everywhere, and V naught minus, which is C times the indicator that R is greater than or equal to K. Because so once we've proved that this holds for those particular initial conditions, then any initial condition V naught, which is non-decreasing and satisfies this, will be sandwiched between those two initial conditions. And we can prove a comparison principle for solutions of the free boundary problem that says that if you start with two initial conditions that are ordered, so if one is greater than or equal to the other everywhere, then they stay ordered in that way at all subsequent times. And so that means that once we've established this for the two special initial conditions, then that's enough. And once we've got this one-dimensional convergence result for solutions of the free boundary problem, then it's not too hard to show the long-term behavior of the d-dimensional free boundary problem, because essentially all we then need to show is that at very large times the solutions of the d-dimensional free boundary problem are close to being spherically symmetric. So the remaining results that I told you about were about the long-term behavior of the particle system itself. So I want to show you the main intermediate result that we use to get them. And again, it's a result just about the distances of particles from the origin. So let's take a positive k and a small positive c. And then if we take a small positive epsilon, then if the number of particles n is at least some n epsilon, and if we look at a time t that's at least some t epsilon, then if we take any initial particle configuration such that Fn of k and 0 is at least little c, so such that the proportion of particles within distance k of the origin at time 0 is at least c, then so we can say that the probability starting from this particle configuration that the supremum over R of the modulus of the difference between Fn of R and T and capital V of R, the probability that that's at least epsilon is at most epsilon, and the probability that the difference between MNT and R infinity is at least epsilon is at most epsilon. So if you remember that MNT was the maximum particle distance from the origin, and capital V and R infinity were the steady state solution of the one-dimensional free boundary problem. So this is saying that if we've taken epsilon to be small, then if we have a very large number of particles and we look at a large time, then with high probability, the proportions of particles at various distances from the origin are given by capital V, and the largest particle distance from the origin is very close to R infinity. So I'll give you the sort of main ideas in the proof of this result. So the proof is in two main steps. So the first step is to show that at a large time s, then with high probability, Fn of k and s is at least c. So what that's saying is that at a large time, then the distance from the origin that we need to go to capture at least a proportion c of the particles is at most k. And the way that we show this is we look at how far we need to go from the origin to capture that proportion little c of particles, and we look at that distance on successive time steps. And we can show, using the free boundary problem approximation, that if that distance is very big, then it's actually very likely that the distance gets smaller after a constant amount of time later. And we can also bound the probability that that distance makes large positive jumps just by saying that comparing the particle system to a branching Brownian motion without any killing. And that allows us to show that with high probability at a really large time, the distance that we need to go is actually at most some large k. So then when we've got this first step, then what we do is we fix a very large constant capital T, and we take a time little t that's much bigger than capital T. And let's suppose that that Fn of k and little t minus capital T is at least little c. So step 1 tells us that if little t minus capital T is big, then this is going to happen with high probability. So let's suppose that it happens. Then there are 2 things that we can say. So the first thing is that we can use our one-dimensional hydrodynamic limit result to say, let's look at what happens to the particle system between times little t minus capital T and time little t. So then we're just looking at it over a time interval of constant length. So we can compare it to a solution of the free boundary problem. So we can say that if n is large enough, then with high probability, Fn at time little t is going to be very close to V at time capital T, where V solves the one-dimensional free boundary problem with initial condition given by the particle configuration at time little t minus capital T. And here we're using the fact that, so I mentioned in the one-dimensional hydrodynamic limit result that our bound on how close the particle system is to the solution of the free boundary problem doesn't depend on the initial particle configuration. So this with high probability and this roughly equals don't depend on the actual configuration at time little t minus capital T. And then, so the other thing we can say is using convergence of the solution of the free boundary problem, we can say that if capital T is large enough, then the solution little v at time capital T is going to be very close to the steady state solution capital V. And we know how big we need capital T to be because we're assuming, so from our definition of V naught and from this assumption at the start of step 2, we're assuming that V naught of K is at least little c, and I said that that was the condition that we needed to know how quickly solutions of the free boundary problem converge to capital V. So
there's another question in the chat.
Yep. Why? So, okay, so that's what we show in step 1. So I sort of tried to skate over the proof. Is the question, why do we need S to be large, or I'm not sure whether I understand. So I mean, so maybe I can say more about how we prove it. So we look at how far you need to go from the origin to capture at least a proportion little c of particles. We look at that on successive time steps, and we can actually bound that above by a Markov chain, and it's a Markov chain that has a stationary distribution that has most of its mass sort of in, well, most of its mass below k. And so that means that we can say that at least at large times, the Markov chain is likely to be below k, or in other words, the distance that we need to go from the origin to capture a proportion c of particles is at most k. Does that slightly answer the question?
But sorry, it seems that for fixed but large k, it have to be small for large s, because the measure is concentrated around origin. It's impossible for large k if k is very large.
So Fn of k and s is the proportion of particles that are less than distance k from the origin. So it's the proportion of particles in this really big ball around the origin. And particles are being killed if they're the furthest particle from the origin. So there's always a sort of pressure for particles to be nearer the origin. So
but k is arbitrary, yes? Or not?
Okay, Okay, now I understand. Right, yes. So sorry. So I've sort of cheated a bit here, and what I should really be saying in step 1 is that so the maximum of k and a large constant. So yes, so this wouldn't be true if I took k to be very, very small, but sort of all the way through this theorem, I'm actually wanting to think of k as being big. Does that make more sense?
Thank you.
So sorry that I can see why that was confusing. Sorry. Okay. So back to step 2. So I hopefully convinced you about these two steps, and if you put them together, what that means is that with high probability, Fn at time t is close to the solution of the free boundary problem at time capital T, which itself is close to capital V. So that tells us that with high probability, Fn at time t is close to capital V, which is what we wanted to show here. And then if we do a bit more work, we can get this result about the maximum particle distance from the origin. So that's roughly how we prove this result. And then how do we turn this into d-dimensional results? Well, we can do a bit more work to get a sort of uniform upper bound on Mn. So we can show that the probability that the supremum for s between 0 and 1 of Mn t plus s, the probability that that's more than r infinity plus epsilon is at most epsilon. So that means if we start at a large time and then we look for a fairly large time interval after that, then by applying this result multiple times, we can say that with high probability on that time interval, the largest particle distance from the origin is always at most r infinity plus epsilon. And so any particle that goes more than distance r infinity plus epsilon from the origin will be killed. And so that means that we can see the Brownian bees on that time interval as a subset of a particle system where particles are killed if they go more than this fixed distance from the origin. And again, this is a particle system that's much easier to control, so we can prove results about its long-term behavior and then transfer them back to results about the Brownian bees. So that's all that I wanted to say about the proofs of our results. And now I just wanted to say a little bit at the end about related work and conjectures related to our results. So first of all, our model can be seen as an example of a class of models introduced by Nathaniel Barosticki and Li Zhao. So they have a fitness function f on the whole of Rd, and they have n particles that are moving according to Brownian motions in Rd. And each time a particle branches, then the particle with lowest fitness value, when fitness values are given by the fitness function of their location in Rd, that particle with the lowest fitness value is killed. So they studied 2 particular examples of this, and actually the examples that they study, they sort of always push the cloud of particles away from the origin. So they see really interesting behavior, but it's very different to the behavior that we see for the Brownian bees. And then another very closely related model was introduced by Luigi Adari-Berri and Jessica Lin and Thomas Tondron. So they study barycentric Brownian bees. So again, they have n particles moving according to Brownian motions in Rd. And this time, when a particle branches, then the particle that's furthest from the center of mass of the system is killed. So it's the center of mass of the system rather than the fixed point of the origin in our model. And they show that the motion of the center of mass rescaled in a suitable way converges to a Brownian motion as the number of particles n goes to infinity. And what we believe should be the case is that if you look at the cloud of particles and recenter it by the center of mass, then actually the long-term behavior should be the same as for our model. So we believe that the density of particles should also be roughly given by capital U, this steady state solution. And then finally, I want to talk a bit about the Nbbm process that Pascal already mentioned. So it was introduced by Pascal, and in this process, you have n particles moving on the real line according to one-dimensional Brownian motions. And each time a particle branches, then the leftmost particle in the system is killed. So you end up with a cloud of particles that gradually moves to the right. So we're going to write, so we're now going to write xn of t for the vector of particle positions at time t. And it turns out that this, the Nbbm is also has a closely related free boundary problem. So this is the free boundary problem. So we've got an initial probability density function rho naught on R. And we've got a pair of unknowns, rho and L. So rho is a function of x and t, and L is just an unknown moving boundary. And we want rho to satisfy this PDE to the right of L, and we want rho to be equal to 0 at LT, and we want the integral of rho to always be equal to 1, and we want the initial condition to be given by rho naught. So it's going to turn out that rho of x and t is roughly speaking the density of particles in the branching in the Nbbm if you have if n is very large, and that LT is roughly the position of the leftmost particle. So then why do we end up with this system of equations? So for the first equation, if you're to the right of LT, then particles are not being killed, and so you get the Laplacian rho from the Brownian motion and plus rho from the branching. And then particles are being killed at roughly position LT, and so the density should be 0 there. And then the third equation is saying that the total mass of particles is constant, equal to 1. So it turns out that solutions of this system of equations exist, and they're unique. And so, as I mentioned before, De Masi, Ferrari, Prusiti, and Soprano-Loto proved a hydrodynamic limit result for the Nbbm in 2017. So they showed that if the initial particle locations in the Nbbm are IID with density rho naught, then if we take an x in R and a positive time t, then the proportion of particles in the Nbbm that is to the right of x at time t converges almost surely to the integral from x to infinity of rho at time t as n goes to infinity. So roughly speaking, this is saying that as n goes to infinity, the density of particles is given by rho. So that is known for the Nbbm. Now I just want to show you some conjectures about the Nbbm. So in these boxes, so first of all, this is the hydrodynamic limit result, which is known. So I'm writing mu n of dx and t for the empirical measure of the particle configuration at time t. So what can also be shown is that if you view the particle configuration from the point of view of the leftmost particle, then it converges as t goes to infinity to a stationary distribution that depends on n. What is conjectured about the long-term behavior of solutions of the free boundary problem? So there's an infinite set of traveling wave solutions to the free boundary problem, but there's a unique solution that has minimal speed, and it's conjectured that if you start with a compactly supported initial condition, then solutions of the free boundary problem converge to this minimal speed traveling wave. So then a natural question is, as n goes to infinity, then does the shape of the cloud of particles under this stationary distribution converge to the shape of this minimal traveling wave? So that would be the equivalent result to our results about the Brownian bees, and it's sometimes called a strong selection principle, because it would mean that the particle system and the free boundary problem both select the same traveling wave to determine their long-term behavior. So then just finally, there are some other nice conjectures about the one-dimensional Nbbm, some of which were mentioned by Pascal as well. So if you take the position of the rightmost particle at time t and you divide it by t, then that converges as t goes to infinity to some Vn. Vn converges as n goes to infinity to 2, but it's conjectured to converge extremely slowly. So Vn is conjectured to be 2 minus something of the order log n to the minus 2. And this has been proved for the n-particle branching random walk by Maillard and Gouret, and also for a related Fischer Kpp equation with noise by Müller, Mitnick, and Pascal. And then maybe the most exciting conjectures about the Nbbm are about the genealogy. So as Pascal mentioned, it's conjectured that if you take a sample of particles and you trace their, at a large time, you trace their ancestry backwards in time. So there are times at which they have common ancestors. So you end up with a coalescent process. And it's conjectured that if you look at this on a log n cubed timescale, then what you get as n goes to infinity is a Boltzhausen-Snitman coalescent. And as Pascal mentioned, there's work of Berestukey, and Schweinsberg, which shows this result for a closely related particle system. So at the moment, proving this genealogy result for the Nbbm seems fairly tricky, but maybe a good first step towards understanding the long-term behavior would be to prove this set of results. So the set of results corresponding to our results about the Brownian bees. So that's it. Thanks for your attention.
Thanks, Sarah, for this beautiful talk. Are there questions for Sarah? Please unmute yourself because I cannot see anybody.
I had a question. I know you're interested in letting n go to infinity, but I'm somewhat intrigued by the process for fixed n and even very small n. So for n equals 1, pi 1, if I'm not mistaken, doesn't exist, and you have to have n is at least 2. Anyway, I'm wondering if you say take n equals 2, how explicit do you know this distribution pi 2? For example, the marginals Gaussian or the distribution between the two particles? What can one say about that?
Yeah, that's actually a very interesting question, and for some reason it's not something that we thought about at all. So I guess they wouldn't have that much forcing them to actually be near the origin. That's a very good question, but I just haven't thought about it at all. So so I'm not sure.
And even like exponential, like if you look at the distance to the further guy from the origin, that this has an exponential moment, that is not known either, that things like that.
No, I mean, I'd be very surprised if it didn't, right? But under pi n, I can't see a way to immediately get that. Yeah.
Okay, thank you.
Are there further questions? I have a question. You had all these variants, and I was wondering if you could have something a bit less independent, in the sense that, for instance, you kill the particle which is at largest distance to the origin with probability p, and with probability 1 minus p, you kill another particle, which you choose uniformly, let's say, just to, and so this would be another variant, right, of this
absolutely
models.
Yeah, and in fact, you can kind of have fun with this. You can do other things where with some probability you can kill the furthest away, and with some probability you kill the closest to the origin. So yeah, there are certainly very interesting variants of the model. I think for your example, then certainly I think you could probably carry over most of our techniques. The one where you might kill the closest one to the origin, I think there's maybe a bit more to do, because you sort of end up with more than one boundary. But yeah, I think if you just killed a random one, then that probably wouldn't be too bad.
And then you would still have that R gets finite immediately.
I think so.
Yeah, I think so. And you probably, I would think that the hydrodynamic limit is not different, actually.
Yeah, I think there'd just be like some scaling factor somewhere that would.
Not even sure about that. maybe the relaxation. I'm not sure.
It's an interesting idea anyway, yeah. So we had thought a little bit about killing the one closest to the origin, but we hadn't actually thought about killing a random one.
Nice. So are there further questions? It doesn't seem to be the case. So then I suggest that we all unmute ourselves and give an applause to both speakers of this day. So we will continue in a week with a session on opinion dynamics, and we will send the announcement the day before, as always. Thanks to everyone for attending.